So thank you. I'm Stefan. I'm working at Intel as a ray tracing software engineer, currently lead of the Embry project, and I'm going to present a bit about SYCL and our experience and achievements with it so far. Motivation for SYCL and the whole thing here is most of us, we have already existing C++ code bases, and there's of course plenty of GPUs around that we would actually like to have that code run on. Some big in data centers, some small in laptops, but yeah, we have code and we want it to run GPUs. That's in general what we want. In addition, we're here for open source, obviously. That's the event of the day. We like open standards. We don't want a vendor lock-in, but again, vendors should actually support what we're doing, and something that's actually tried and tested and not just something that is still very experimental and early and nobody knows if it works. So for this, I would like to introduce SYCL as a vehicle for doing this. Probably not everyone's too familiar with SYCL. It's a Khronos open standard, one of the lesser knowns, I think. And it's a cross-platform sort of compiler, API, kernel language that is intended for accelerators of any kind. So GPUs can also compile to CPU, FPGAs, etc. It is intended to be fully on C++, so a C++ first language, and for single source, so you can write your host and device code in one and the same file, and heterogeneous compute, so you can also mix and match these devices. There's a whole bunch of implementations out there already. The one that we provide is in our oneAPI framework. It runs mostly on Intel CPUs, Intel GPUs, but provided by CodeBlade, also has backends for CUDA and HIP. There's adaptive CPP, and then there's a whole bunch more that are partially academic, partially esoteric. Some are by special hardware vendors for their own FPGA or something like that. Focus today for me is mostly on the oneAPI implementation, but not limited to it. Now, we've heard this one before. You write your code once and it runs on all the GPUs, it's just fine. And OpenCL was promising. I don't know what everyone else's experience with it was. I started out very hopeful and ended up being, somewhat disappointed with the results. Implementations, how people actually follow the standards is a bit all over the place. Yeah, it was not as satisfying as we hoped it would be. So now what's different this time? Why is this not OpenCL 2.0? Well, it's a single source programming model, so we don't have this whole separation between kernel and host. It's also not in like separate OpenCL C kernel language and then host in C++, and you have to re-implement your data structures maybe twice, make sure your data types are the same size and everything. It's something you just do in one place. You have the same include headers and everything, and it just works. It's also C++ integration, so you have templates, you have Lambda captures, you have all these things that we tend to use these days now that are just standard open C++ and that are missing in some of the kernel programming languages that are around in graphics. The queues and memory and all this management is on a higher level abstraction than in OpenCL. It's not as low level, so you can get started fairly quickly. It reduces the overhead that you have in boilerplate code. And the error handling is also in the C++ world. You don't have to constantly ask it, like, do you have an error? But you can use exception handling and catch these errors this way. And one of the advantages that I actually liked that I found troubling with OpenCL is that you can compile on your machine and not the driver on the user's machine. So there's not that many surprises anymore that suddenly what you considered valid syntax and your compiler considered valid syntax, the latest driver on the user's machine did not consider a valid syntax for whatever reason, whatever missing extension. And this you can now compile directly on your machine down to all the targets that you want to have, and not like need to install a driver for all the machines that you actually wanted to compile to, because the driver itself is a compiler. And this would in the oneAPI version, we support compiling to SPIR-V, we support compiling to PTX, there's LLVMIR, or you can go directly to the SASS, it's Nvidia, I think, our Intel Gen assembly language, or to, I don't know what the name of Nvidia's RDNA architecture, AMD's RDNA architecture assembly is, but you can also target that directly and compile it on your machine. Vulkan is also sometimes being tossed around as your cross-platform compute API. But then again, differences are, again, we have C++ in the kernel. It's a standardized kernel language. You have a single source model. You have, especially compared to Vulkan, managing queues in memory is a lot more simplified. You can just pass pointers from host to device code and back. Your data transfers are being handled for you. You have CPU support. And some of these things, you can get these on Vulkan. There's actually Silicon, I think it's called, that implements SYCL on top of Vulkan. So some of these things you can do in Vulkan for sure. But SYCL itself is, I think, a bit more convenient. Now, for the conciseness of this is a minimal SYCL example. And you don't have to do much in terms of querying devices. You have a malloc shared. That's just a simple malloc, and this pointer you can use on the host and on the device. You don't have to pass kernel arguments individually. They're being lambda captured here. So you can see that the parallel 4 is what runs on the device. And yeah, just writing numbers to a buffer here is a simple example. And you don't have to do any special buffer management magic. You just have a pointer that you pass in, and the pointer comes out, and the memory transfers in this case are being handled all implicitly. Our Intel oneAPI version of this is based on the LVM Clang compiler. It's a fork, and we're trying to upstream as much as we can. For the host compiler side, you can actually have your host code still compiled with the same compiler that you're using before. So you don't have to switch all of your code to Clang. You can just have the device code being compiled with our Clang version and still use Visual Studio or GCC for your host code as you have. So there's no surprises there that things need to change in too many places. The backends that are listed here, I'm actually skipped our FPGA backend because it's, I don't think, relevant here today. But we can compile to CPU, OpenCL, and SPIR-V as a more generic version. You can go to Intel GPUs with SPIR-V and Level 0. And we have, courtesy of CodePlay, we have backends for CUDA and HIP. The entire compiler stack is available open source at GitHub Intel LLVM. You can download it and build it yourself. And I guess I should point out we have if you download the oneAPI toolkit, it is not exactly identical to the open source version. Major difference being CPU compiler changes, CPU compiler improvements that we have out of the existing Intel CPU compilers that are being merged and being used in that. But for the purpose of the SYCL talk and SYCL, these compilers are largely identical. Now the Nvidia and AMD backends, they still all use the same SYCL compiler frontend. So if your source code compiles on one, you can know that it compiles for the other. It's not going to be any different parsing or different headers for the whole thing. And we still go to a common LLVM intermediate representation. And only from there we go to different backends. Nvidia is going to PTX, which is the PTX backend that's in LLVM. And then the CUDA toolchain PTX assembler compiles it onto machine code. Likewise, AMD is using the backend that is also part of LLVM, which to my knowledge is actually provided by AMD for the HIP compiler. I believe it's the same backend. Runtime side goes just to the native APIs, and it's a thin wrapper, fairly thin. So it's a create a queue, allocate memory, copy memory, wait for events. These things just being wrapped one layer, so it's a bit of an abstraction in between. You can always get these native objects back with interrupts, or you can construct SYCL objects from these native objects. So if you already have a CUDA application, you can just use that CUDA queue and pass it in there and just use it as a SYCL queue, or memory buffers are easy to exchange this way as well. Hardware-specific features can be exposed as extensions, and the extensions that we have are not just only for Intel own. So we have, for example, an extension to use the explicit LDG Nvidia texture fetch to the cache. You can use this as a SYCL intrinsic, and naturally it will only work on NVIDIA hardware, but it's still something you just write down in regular C++ code. I'll believe it when I see it. This is as far as we went that you just have in Blender cycles. You can build it this way. And we actually built that triple GPU machine that had GPUs from all vendors. You could turn them all on, and they will all render simultaneously on the same frame using the same source code. I could show an image of rendering, but it just looks like a renderer being rendered. So, for those not too familiar with Blender and cycles, I'm assuming everyone here knows what Blender is, but the cycles renders maybe not everyone's familiar with. It is a physically based path tracer, and it started in 2011, back then as a CUDA and CPU renderer. And the initial version was just a giant mega kernel implementation that later was refactored to a wavefront microkernel approach to just address many of the problems that I think we all experience with the big mega kernel ray tracers. And even then, it's still challenging. It's I think the shading code still compiles down to 120,000 instructions or something. But overall, the breakdown into wavefront microkernel approach is a common thing that everyone did. And around that time, initially it had an OpenCL version that was provided in Blender versions, but even then already it had to be broken down to smaller kernels because the OpenCL compilers at the time could not actually deal with this massive code base. And even then, when it was broken down, it was still very fragile. It was still that introducing new features could suddenly trip the compilers, and things would not work anymore. They would work on one platform, not on the other, and it was highly sensitive to driver versions. And it was a discrepancy starting between the OpenCL and the CUDA code. They became too separate, and it was not a good thing to maintain anymore. And this is a quote: the combination of the split kernel implementation, driver bugs, solved OpenCL standard has made maintenance so difficult, and so they decided to drop the OpenCL backend with that refactor to the wavefront approach. So the wavefront kernel was then released with a CUDA HIP and CPU support. And for the release of the ARC GPUs at Intel, we provided the SYCL backend that then came out in the version 3.3 release. The builds that come if you download a binary of Blender are only compiled for Intel GPUs at the moment. And they come pre-compiled with the hardware that we ship, so you don't have any JIT compiles and wait times at the time. So it should run pretty fast out of the box. But if you download the source code from Blender and build your own, you can actually turn on the Nvidia and AMD backends, given that you use a compiler that can do it. And then you can use these simultaneously, and the results that we get are about as good as you can get them with fast math enabled. So it's not bit by bit identical. We use, for performance reasons, we use the lower precision inverse square and sinus, cosine, all of these. So it's not the bit by bit identical one, but it's close enough. It's about the discrepancy that you see between a CPU and a GPU implementation typically. Specialization contents for reducing the amount of source codes being compiled are being used on the platforms that support it. I think it is only Intel right now, but there's nothing that would, from the source code side, stop it from being used anywhere else. And the result is pretty much as you would have native code. This is SYCL source code on the left side. On the right side, it's NVIDIA assembly. This is inside the Nsight profiler. So you can use, if you compile and run it on NVIDIA, you can use the NVIDIA tools to debug and to profile it. On Intel, you can use vTune to debug and profile it, so you're actually expanding your tool base by using this cross-platform thing, which sometimes may be useful if your one debugger profile doesn't catch it, maybe the other one does. In terms of performance, we had the people at CodePlay did a bit of a deep dive in optimizing the CUDA code, and here we're comparing yellow bar is running the SYCL code in oneAPI, and the green bar is the NVIDIA performance if you run it same hardware, but CUDA source code and CUDA compiler of the cycles renderer. And these are 96%, 97%, 96% of the performance you would get from the native Nvidia backend. And possibly there's still something left that you could extract out of it if you were to put in some more optimization work. Most of the optimization that was necessary was being a bit more selective about what is being inlined and what is being unrolled. On the AMD side, we didn't do the optimization yet, so compared to HIP, the performance is not as good yet, but it was also that we didn't do that deep dive into optimizing it. And I would expect that there's still room for improvement that we could do there. And a bit of the missing part that we have is hardware ray tracing support. On Intel, we can do hardware ray tracing because the Embry library just ships with SYCL headers and SYCL implementation, and you can use basically the same API as you have on the CPU already. And then you get hardware accelerated instances and BVHs and triangles, and the rest is in software using pretty much the same source code as the CPU implementation. So hair intersections and sphere intersections are pretty much the same. And we're using the RTC intersect and synchronous ray tracing, so you don't get the hardware reordering of and sorting of rays, but it makes the porting of your existing CPU much easier if you just use the same programming model, the same flow. And we did experiment with, like, can we also get other hardware acceleration into SYCL? And an internal test that we did was actually porting Embry on top of optics, so that you would actually have SYCL code, it compiles the PTX, and then we feed that PTX into optics, and the runtime that we have for SYCL, we slightly modified it to use the optics launch. Since mostly you can use CUDA context and CUDA memory, it was not that much of an overhead. It had to do a little bit of transforming the PTX to be in a way that optics expects it, but it actually runs. So it is possible you could have third-party hardware ray tracing in SYCL as well. If you want to compile this for yourself and try it out, you need the Intel LLVM compiler that you can download from the page I had earlier. There will be a link at the end too. You can compile it with the Nvidia and AMD backends, and then only set a few CMake options in the Blender CMake files, and then you're off and compile it. Only at the end, when you run Blender, you need to explicitly enable that the driver, the implementation, will actually show you all these other devices because they're not tested and not supported. We don't expose them by default. It's an environment variable. You need to make it so that they actually show up. But that's basically all that you need to do to test it yourself. So moving forward, at the end, our call to action would be, feel free, try it out with your own source code, see what happens. And most importantly, I think if you like it, if you want this, then talk to other hardware vendors. Like, I'm at Intel, and you wouldn't want me to write your Nvidia compiler. You wouldn't want me to write your AMD compiler. Even if I did the best I could, you wouldn't trust it probably. So talk to the people that make the hardware and make the compilers and tell them you want to support it. Since there's already an OpenCL backend and a compiler that goes through SPIR-V, I think it's not that hard for many people to go there. Like, the big components are in place, probably 90% there already. And if you want, you can contribute yourself. You can also, it's an open source project, the compiler, build it, modify it, make pull requests. Again, the two links, QR codes if you need them, to Blender source code and the compiler source code, and feel free to try it out. And I think that's it that I have. Thank you for your time.